Okay, so let's start the next session. So for our next speaker, we're very happy to have Igor visiting us from very far away. To tell us about Ginzburg Landau description of some non-unitary minimum models.
Yeah, thanks a lot, Simona, and thanks again to all the organizers. Actually got added to the schedule only a few days ago, and somehow was not subtracted. Yeah, one thing that's clear from the talks I've heard so far, which have been really interesting, is that the Ising model still reigns supreme in the field of critical phenomena, and maybe some ON models also are on the list. And I want to add a couple more entries to the list, to the agenda, so to speak. On a whim, I added these two pictures. You can gather from the title who they are in case you don't know. Or maybe just to add some gravitas to my talk. And in fact, Ginzburg, I saw in person. He visited here in the late 90s and gave a colloquium actually about his recollections of Landau. And Landau, I heard some first-hand accounts as a kid of what he was like when he worked in Kharkiv. Okay, so, but I should also say that perhaps a more appropriate picture on this would be of Sasha Polyakov, but luckily he's here in person. So the talk will be based mainly on these papers, one going back to over 10 years, and then I picked up this thread in these two much more recent papers. And so minimal conformal theories in 2D that were introduced in the landmark 1983 paper by Belavin, Polyakov, and Zamolodchikov. And I've been just for fun looking again at this paper. They basically found an exact mathematical solution of an infinite class of, as said in their abstract, massless interacting 2D field theories. They call them minimal conformal theories. Now people mostly call them minimal models in 2D. But as I will mention in a second, at that time it was not clear what these theories are. Like, basically, the reason I added Ginzburg Landau to the title is the idea of effective field theory of second-order phase transitions. Like, what is their formulation in terms of scalar field, some kind of semi-classical effective Lagrangian? That was only available at the time of writing of this paper, basically, for the 2D Ising model. If I'm just reading the paper, maybe Sasha knew more. He often puts not everything he knows in the paper, but so these MPQ, that's the notation for minimal model labeled by P and Q, co-prime positive integers. They have this Virasoro central charge, very well-known formula, and they're characterized by a finite number of Virasoro primary fields, phi RS, and there is a famous reflection relation for these exact conformal holomorphic scaling dimensions. The full scaling dimension is H plus H bar, holomorphic plus anti-holomorphic, and the spin is H minus H bar. Okay, so in the original paper, the M34 was identified with a critical Ising model in 2 dimensions, and there was also a footnote that there may be some similarity between the M56 and the 3-state Potts model attributed to Datsenko. Apparently, Datsenko noticed that some scaling dimensions look the same. But for other models, the big next step was made by Zamolodchikov in 1986. Basically, the unitary theories are the ones where P minus Q is equal to plus or minus 1. So they're labeled by consecutive integers. And Zamolodchikov proposed this effective scalar field theory for the A-series minimal model. A-series means that there is a diagonal modular invariant and all the primary fields just have been 0. And it's just this very simple looking scalar field theory generalizing the 5 to the 4 massless theory. And for example, if you look at M45, which is the tricritical Ising model, that would be 5 to the 6. The theory whose upper critical dimension is 3. And then you go to the A series M56 will be 5 to the 8. It turns out that the Potts model is actually the first D series model because it contains a spin, so its effective field theory is somewhat different actually for the 3-state Potts model. For these unitary models, basically the situation was already largely clear back in the 80s. But most minimal models are non-unitary. And the simplest one, M25, was identified by Cardy in 1985 already as the Yang-Lee critical point, whose Ginzburg Landau description was found by Michael Fisher before all of this. In the late 70s, basically, he was studying the, the cubic theory and found that the upper critical dimension here is 6, and in 6 minus epsilon dimension, he found that the infrared fixed point is at purely imaginary G. So this purely imaginary G immediately solves the problem of stability, because if G is real, of course, the theory is not going to be stable and will just roll off to infinite phi. But for imaginary G, it oscillates very rapidly. And so this whole Yang-Lee universality class has to do originally with studying the model in imaginary magnetic field. For example, studying the 2D Ising model in imaginary magnetic field, Yang and Lee found the famous Yang-Lee zeros of the partition function. And the criticality has to do with the accumulation of these zeros near some edge singularity. And then some people call it Yang-Lee-Fisher because Fisher basically discovered what is the effective field theory for this critical phenomena. And this also opens the way for studying higher dimensional generalizations than 2, because this theory is critical not just in 2, but in 3, 4, and 5 dimensions. So the delta phi, so what Sasha and collaborators told us is the exact dimension of the phi field is negative actually at this point, is delta phi is 2h12 is minus 2/5. So this means that the 2-point function actually grows with distance, very peculiar behavior. And this, so people are now having great fun computing higher loops. So the epsilon expansion actually is known at least to epsilon to the 5th order. I'll mention this later. And the match, extrapolated match is pretty good. It's not great, but it's really looks like it's not far from there. Now one can also consider just two-field theory, basically a direct product of these two models. It was discovered already long ago that this actually describes minimal model M310 on the D series. Just this very, so all the scaling dimensions in this model are sums of certain scaling dimensions of the M2,5 model. Okay, so just looking at this model, this M310 model, the modular invariant contains some spin zero fields, but also contains some higher spin fields because there are cross terms in these characters. Here is a little table listing the spin zero fields, and one can match them pretty nicely to the field theory with these two fields, phi1 and phi2. Some are Z2 even, some are Z2 odd. And then there is also something people call PT symmetry, although it's a bit of a misnomer. P here stands for a symmetry which just interchanges phi1 and phi2. and T acts by I to minus I. It's an anti-unitary symmetry. And for example, the match actually it's pretty interesting and works nicely. For example, one of the fields phi 19, which has exact dimension 4, it's really the stress energy tensor of first model contracted with the stress energy tensor of the second model. And then there is also a spin 2 primary, which is a difference field. Of course, the sum of them is a descendant. They're sort of descendant, but the difference is a spin 2 field, which is this phi 19 and phi 19 bar. And there is also a primary field of spin 1 contained here. Okay, so this is fun, but I'll try to tell you something a little more interesting, which is there is another theory which is basically obtained by RG flow from this model and is a similar theory. But before I do that, let me just, to honor many other talks at this conference, do a bit of a detour into the ON model. And this also explains how we got into this. You may wonder, why am I doing this? Right? I mean, this is not something I was trained to do in graduate school. And actually, I kind of largely missed the great conformal revolution of the mid-80s. I don't even own the yellow book I recently but somehow, so I'll tell you, it's a bit instructive, like how I got into this. So the ON model is, of course, we all saw it already in many talks. It describes, it's particularly interesting in D equals 3. For n equal 1, it can even go to D equal 2. And now we have a variety of techniques and cross-checks, the Wilson-Fisher 4 minus epsilon expansion, the nonlinear sigma model, the 1 over n expansion, numerical conformal bootstrap, and now added to this is this added entry, the fuzzy sphere, which is largely why this workshop is taking place. There is a lot of news from the fuzzy sphere. So the 4 minus epsilon expansion is the one loop beta function that's in Peskin and Schroeder. You find the infrared fixed point and can start developing epsilon expansions for dimensions of fields like pi and pi squared. Now available up to 6th order, as we heard from the beautiful talk by Bill Pennell yesterday. Then there was a question, what about negative coupling? Actually, Szymanczyk in 1972 thought of this model as actually asymptotically free model, the simplest asymptotically free model, but it's only metastable. There are only metastable fixed points in 4 plus epsilon dimensions. Making n large helps stabilize them, but there are still some tunneling instabilities that add small imaginary parts of order e to the minus n over epsilon. And this was done in a very nice paper by McCain et al. In '84. And we actually, with Simone, Silvio and Grisha and Richard Huang, a former undergrad student, we extended this to the range between 4 and 6 dimensions.
Just to understand, these affect offend the conformal symmetry or the unitarity property? I don't understand.
Yeah, they're not strictly unitary. These models, just a naive worry that you will like fall off the minus 5 to the 4. It's there, right? Yeah, you can think of them as an example of a complex CFT, perhaps. But one thing that actually, after we worked on this, we started doing this in 2014, and people did bootstrap in 5D and actually saw islands. And the reason people might see islands for a while is because you can make the imaginary part of scaling dimension very, very tiny, like 10 to the minus 16, and the numerical bootstrap will not detect it. So yeah, it's still like very interesting to see these very close to very, very weakly first order transition, perhaps. So the reason actually we started working on it is because of the higher spin ADS-TFT. With Sasha, we conjectured that the ON model in 3D at large N is dual to Vasiliev higher spin theory in ADS4, and this was one of the motivations in mind. So the 1/n expansion of the CFT is generated by introducing this Hubbard-Stratonovich auxiliary field. That's a very standard technique. You then integrate out phi to give effective dynamics for sigma, and you get this kind of induced dynamics for sigma. In real space, sigma is basically what replaces the phi squared field in this formalism, and you have indeed the 2-point function going like 1/x minus y to the 4. Yeah, the first paper we wrote was with Simone Giombi and his student Lin Fei in 2014. And actually the 1/n, for example, you can compute 1/n correction to scaling dimension of phi. The leading correction comes just from the self-energy diagram, including sigma, where you attach a sigma line to phi propagator. This expression was known from long ago. Yeah, I'm not sure totally what is the first paper where this appeared, but it was sometime in the 70s. But recently we heard interesting news about this formula, actually from Ludo's talk yesterday, was that this formula can be very neatly derived by maximizing the sphere free energy F tilde in this model. It's, I think, quite a beautiful little calculation. And one of the connections with the sphere of my talk. But then I'm not just saying, so what people noticed actually even long before us is that this leading 1/n correction changes sign in 6 dimensions, but between 4 and 6, it still stays positive. So once it changes sign, the large N theory is certainly non-unitary, but there was a question, what if it's somehow unitary between 4 and 6 dimensions? And this question actually occurred to Giorgio Parisi already in 1975. And it turns out that the theory is basically unitary to all orders in the 1/n expansion, but only these instanton effects violate the unitarity and make dimensions complex. So this is the interesting range between 4 and 6 dimensions. Of course, 6 is, and then we came with this idea to write down a cubic ON symmetric theory that would describe the 6 minus epsilon expansion of this theory. So this is actually, for me, was a bit of a change of my scientific life, because I didn't do much regular normalization before. But then we started working on this very simple ON symmetric scalar field theory and discovered a whole bunch of neat things about it. For example, so if you just write down the coupled beta function equations for this theory, they actually have real fixed point for n bigger than 1039, believe it or not. Then life gets uninteresting between 1.02 and 1039. It's not very interesting. And then gets it even more interesting, perhaps. So this is, for example, the flow pattern for n equal to 2000. There are 2 fixed points, but then for n less than 1039, they sort of merge and go off to complex planes. So once you go a bit below 1039, they're just complex, not real, not imaginary, but complex.
But that's just that one loop, though, right?
Yeah. Then, but higher loops don't fully cure this.
But it goes down drastically, right?
Yeah. But I mean, once you realize that there is this small imaginary parts, that kind of, it can't be like a regular second order phase transition that that Ginzburg and Landau from my first slide would want to see. But it's still like interesting to think about what really goes on, for example, in 5 dimensions.
Is the number 2000 unnaturally large, or was there some factors in there that?
I think there are probably some 4 pi's explain it. Yeah,
It doesn't solve the naturalness problem.
If you just push, so we started doing higher loops thinking that maybe this critical n will go down, and it does seem to go down. For example, the bootstrap calculations saw some transition and behavior for n around 500, but it's still a few hundred. So with 2 brilliant graduate students, Lin Fei and Grisha Tarnopolsky, we embarked on a 3-loop calculation. Alas, I did almost none of this. But the formula turned out to be correct and were then quickly checked by experts to 4 and even 5 loops. So what is the use of this stuff? Well, you can say one interesting use is that since we know the 1 over n expansions, we actually know, for example, the 1 over n term to all others in epsilon. So then you can compute it, say, to 17 loop order, and this actually we can predict what the epsilon to the 17 term will be in this particular theory. And this was used, for example, in this remarkable 5-loop paper by Barinsky et al. To cross-check their results. So at the very least, it gives you like a nice check on what these super experts in higher loop are doing. But so now the detour is ending. The detour is ending with the observation that actually, if you go to n below 1.02, suddenly pure imaginary coupling constants appear. So for n equals 0, this is just Fisher's fixed point. But for n equal 1, there are 2 of them. One is the G1 equal G2 decoupled fixed point, which turns out to be after you say sigma is phi1 plus phi2 and phi is phi1 minus phi2, it just reduces to, so this decoupled fixed point becomes this one, becomes just this theory. So that describes this M310 model on the D series. But then there is another, but this is not the most stable fixed point. And there is another coupled fixed point where G2 is about 6/5 G1 plus order epsilon. And this was actually the IR stable one. So we saw the RG flow from between 2 different fixed points. And we somehow tinkered with it and made a wild guess, which in retrospect turned out to be good, that this is somehow M38 non-unitary universality class. It's certainly non-unitary because of imaginary coupling constants. But was really, at the moment, we got lucky. Otherwise, we would have to be apologizing for it. But yeah, we actually thought pretty hard between M37 and M38, and luckily preferred M38. As you will see, M37 would have made no sense at all. But I should have known that then. But so here is the field theory again, which describes this both M310 and M38 with imaginary G's. It has a PT symmetry. P just acts on the field, sigma to minus sigma, and T acts as I to minus I. And the claim is that the continuation of the coupled fixed point gives you a D series M38. Why D series? Actually, it's very easy to see why, because with 2 scalar fields, you can write down the spin 1 primary, sigma d mu phi minus phi d mu sigma. And this invariant contains in this cross term here a vector field. So then in a paper a couple years ago with Zimo, Sun, Grisha, Vladimir Avlansky, we looked at epsilon expansions armed with these 5-loop formula. And indeed, M38 looked pretty good, but it's never so great if you have to shoot from 6 minus epsilon all the way to 2, right? But one thing we realized back then is that there is another important constraint called C effective theorem, that there is a quantity C effective, which already showed up in some earlier talks, which is C minus 24 minimum dimension. For unitary theory, C effective is same as C because the minimum dimension operator is the identity. But in these non-unitary minimal models, H min is really negative. For example, for the Yang-Li, it's minus 1/5. So, and in fact, for all the minimal models, C effective is a positive quantity, 1 minus 6 over PQ. And we noticed that while this flow from 310 to 38 violated the usual C theorem, it actually obeys this modified C theorem by a little bit. So it's in some sense a nearby flow. And for non-unitary models, the C effective is actually the golden quantity, which determines the thermal free energy, which I think was already noticed by Itzekson and collaborators in the mid-80s. And more recently, it crops up in the entanglement entropy.
Sorry. So the central charge will never flow to a complex number.
Yeah, I'm just, yeah, for all these non-unitary minimal models, they're non-unitary still in the nice sense that all scaling dimensions are real, all the central charges are real. The OPE coefficients are sometimes imaginary, the pure imaginary, that's how you see. So the squares of OPE coefficients can be either positive or negative. But yeah, I don't know what the complex central charge. Yeah, I guess it shows up lately in this Rasara minimal string, and but we don't see it here. We don't see this here.
Question?
Yes.
What is the status of this C effective theorem?
Well, so the claim is it was proven by Alala, Castro, Alvareda, Benjamin Doyon, and Ravanini just a few years ago, in 2017, by using the idea of PT invariant flows, that the flow preserves this symmetry. I think they use this symmetry. Yeah, it would have been nice to actually have someone talking about this proof, but maybe next workshop. Yeah, like for us, definitely the whole flow preserves the symmetry because we flow along the imaginary values of G1 and G2. Yeah, I think some ideas about the C effective cropping up were already in much earlier papers already, of course. But so this is the, so basically Belavin, Polakov, and Molochikov gave us this magical machine for solving an infinite class of theories. And we think that apparently it solves this particular theory in 2 dimensions. And the identification of the spin zero fields is basically pretty completely fixed. You just write these expressions. 517 is the operator that mediates this flow, perturbative flow. 515 gives mass terms to sigma and phi. And there is only one odd field, only one Z2 odd field, phi, which is present here. So everything seems very nailed down for the dictionary between minimal model and this effective field theory. And one new thing that we did in this recent paper with Zima-san and Andrei Katsevich is to look at the anomalous dimension of this unique vector operator. We did just one loop calculation of its dimension, and remarkably, it gives a value which is about 13% off the exact value in 2 dimensions, exactly. I know there are some extremely powerful people who can do higher loops, so maybe just a humble suggestion that maybe it would be interesting to look at it.
Igor?
Okay. Yes.
From the M3, 10, are there integral flows that was studied?
from M3 ton.
This one you're something you studied before, right?
Yeah, this was not actually studied before directly in 2D. That's what I'm coming to. Like there were some families of flows. Yeah, so Andrei Katsevich actually studied the flow from M310 to a massive phase just by adding masses. But that was just very recently. But
Igor,
yes.
Can you remind us what the potential is? The potential term for this problem?
Yes, yeah, it's just completely cubic. So there are two fields, and there is a Z2 symmetry acting as phi2 minus phi, and this fixes you to only two possible cubic operators, sigma phi squared and sigma cubed. It's basically the same as our ON model for n equal 1. We did this large N ON model, and then we fixed n equal 1 and found these purely imaginary fixed points here. Yeah, if you throw out phi field, you get back to Fisher's effective field theory for Young-Lee. Okay, so right, so this seemed like a bit of a curiosity, but then there was a paper appeared by Nakayama and Tanaka. Yeah, sorry for the typo. They pointed out the following thing that actually we were not aware of, that we may have done something more interesting than we thought. Because apparently there are these families of flows that people studied in the 80s and 90s. The first one is a Zamolodchikov flow. It's a K equal 1 family, I equal 1, the unitary flows. And then Ahn and Lessig studied I equal 2, like basically you just flow from Q plus 2 to Q minus 2 here. And these K equal 2 flows are all non-unitary. Then there are K equal 2 flows that were studied in the early 90s, these two papers. But somehow this 310 to 38 is the first example of a K equal 3 flow, as it turns out. And no K equal 3 flows were known or studied before in 2 dimensions. I'm not totally sure why, but for us, it was kind of staring in our face if you do it in 6 minus epsilon dimensions. And it corresponds to the first member of the K equals 3 family with Q equals 3 here and I equal 1. Yeah, like you get 9 plus 1 is 10 and 9 minus 1 is 8. So, but Nakayama and Tanaka came armed with much more powerful mathematical apparatus in 2D, which involved line operators and these quantum dimensions corresponding to line operators. I don't feel so qualified talking about this, but they showed that there is, for example, the ground state matches the quantum dimension corresponding to topological line operators at the UV and IR, not just for our flow, but for all of these flows. So they have an infinite family, a new set of families. K equals 3 is the short hours and generalizations, but then there are K equal 4, 5, and even half integer Ks are possible sometimes. And actually, Ken Kikuchi pointed out an interesting monotonicity property of all these flows that the dimension of R comma 1 primary field always decreases on these flows. And I think this was supposed to happen based on this non-invertible symmetry. But then directly in 2D, the Hamiltonian truncation is a useful approach to this RG flow. And recently, Deluche, Elias Miro, and Ingoldsby applied it. It's a very low order calculation, and it requires renormalization. Actually, one thing, this conformal truncation method needs renormalization, so it's a bit complicated. So maybe the fuzzy sphere will help, as actually Grisha will talk about some of the fuzzy sphere stuff. Another check of our Ginzburg Landau description is that there is a K equal 2 flow from M3A to M34. which was already studied in the 90s and 2000 using some method called nonlinear integral equation, which is not quite integrability, but it apparently works. And they actually were plotting C effective as a function of scale and seeing how it's non-monotonic somehow. But from our effective field theory, it's very easy to see why this flow is possible, because there is a term sigma phi squared, and phi 1 phi is just sigma squared. So you integrate out sigma and you get phi to the 4. So you flow to the Ising model. So,
Igor?
yes.
So there are two signs for this deformations. I mean, assuming the operator is.
Right. There has to be one particular sign, I think. Yeah.
Do you know what happened to the other sign?
Like a massive
Massive phase?
Yeah, I think the other side probably.
And this is also true for the Nakayama flows?
Yes, sometimes you have to. Yeah, they were not specific about signs or even eyes.
Yeah,
like
they're just using constraints from the symmetry.
Right. Like sometimes you actually need to multiply this by I just to make sure it's PT symmetric flow. Okay, so then with Andrea and Zima, we enthused by this infinite set of additional flows, we tried to guess what would be the Ginzburg Landau formulations of, say, higher k equal 3 ones, like 3k plus 1 to 3q plus 1 to 3q minus 1, came up with a proposal for odd q, which is also PT symmetric, and it involves not theories with sigma to the sigma cube interactions, but higher ones, like sigma to the 5th, sigma to the 7, and so on. And actually, for q equal 5 and 7, the explicit beta functions were known, were derived by Gracie, and indeed have fixed points with imaginary couplings. Their upper critical dimensions are listed here. They're non-integer for higher ones, but still one can do epsilon expansion and so on.
So for this proposal, what is the modular invariant? And probably there are multiple choices. Do you specify?
Well, the modular, yeah, they're the theories.
Still D
Yeah,
series.
D series. Yeah, because yeah, they have to have higher spin fields. Yes. Yeah, we tried to match fields a bit with 514 and 516 and 514 in our paper, but there are a lot of fields, and yeah, I feel like this 3,8 is very beautiful matching, which is completely nailed down by symmetries and already non-trivial. Here, one has to work harder. So I hope you will look at this paper and just see what the tables are. And okay, so I've reached the end. One comment is that the epsilon expansion of the sphere free energy for these Yang, Lee, Fisher, and M38 were in our recent paper on epsilon 6 minus epsilon expansion of sphere free energy. But the big question is, there are many other PT symmetric non-unitary field theories that are exactly solved by this machinery of BPZ minimal models, and we want to find more explicit examples. But also, we want to understand these critical theories and RG flows more directly in 2D and 3D. And as you will now hear from Grisha, there are spin chain models and now various discretized sphere models, which look very promising. So I think I'll stop here. Thank you.
Yeah, so that's when you have this parameter m, so does the large m limit help you organize or solve some of these flows more easily?
Oh, you mean for unitary models?
Yeah,
Yes.
yeah.
Yeah, so there, of course, for large M, you can use conformal perturbation theory, right? That was done by Zamolodchikov. He computed the difference of central charge, CUV minus CIR, and found that it's of order 1 over m cubed. So it's very beautiful matching there. What happens actually for these k bigger than 1 flows, there is some kind of conspiracy that prevents this conformal perturbation theory from being parametrically reliable. Because the difference of central charges, yeah, we can, for example, take, so with this family, we can take the limit of large Q here. But the difference of central charges is only of order 1 over Q. And what happens is that the 3-point function of 517 with itself actually becomes very small. It itself goes like 1 over Q rather than stay of order 1. And that's why you cannot do parametric conformal perturbation theory somehow. So there needs to be something better, but
I have a question. So, so the flow, you basically flow to the IR fixed point, which could be complex, but will you require the UV fixed point to start with is a real or complex?
Well, they're complex in a very controlled way, right? They're not like complex in the way that you want them to be. Like they won't have complex central charge, for example.
Yeah. So what I mean is that
they do have a the interaction terms have an I in front of them, and they have this combined symmetry under I to minus I and a certain field reflection. So that's the extra symmetry that ensures that I think this will figure very prominently in Grisha's talk. This extra symmetry guarantees a lot of things.
Okay.
For example, that the scaling dimensions are either real or they come in complex conjugate pairs.
Yeah, but the coupling constant as starting point of your flow are real or
no, they're pure imaginary.
So it's a non-unitary flow to a non-unitary.
Yeah, it's inherently non-unitary flow, right? Okay. And because there is this I phi cubed, the simulation has a severe sign problem. So unlike the usual easing model in 2D, which you can throw in the computer and apparently get good results, this model you cannot do this. So you cannot just throw this on the computer.
But is it possible to flow from a unitary to a non-unitary model?
I think so. Yeah.
Or factorizing to the Young model, for example.
Yeah, there are such. Yeah, within this list, this all-encompassing list. Yeah, it's not totally clear if there is more than this because people were trying to generalize this, and it's now. Well, this paper only appeared a few months ago, so I think there is some activity trying to see whether there are additional flows that make sense or not.
And definitely there is a flow from M4 to M25, which is not here.
Yeah, I forget. Okay.
There are a lot of flows which are more, but
Yeah, there. But isn't this one of the k equal 1/2 flows?
No, we need to turn on two operators, massive and magnetic field, and with several linear combination.
Which of these M models on the list? So this is the entire list that you're aware of, right? Is MKQ minus.
Yeah, this is the entire list of their flows, right? And
the CFTs are this construction leads to the A modular invariant, and when does it lead to?
Yeah, I think they were not specific about this. I think all of them certainly have A modular invariants. So these flows should apply to A modular. But when you can do the orbifold to go from A series to D series, what we found is very specific to D series flows.
And among yours, so you have only D series.
Yes.
And among them, there are two kinds of D series. Those where we have only off-diagonal couplings, and those where the chiral algebra is extended. The partition function is either kind of off-diagonal or it's still diagonal in terms of a bigger character.
Oh, yeah, you'll have to tell me more about this. Yeah, I mean, let's see, for example,
So the example you showed is when it's off-diagonal.
Yeah, this is off-diagonal.
But there are other kinds where the pattern is different.
Yeah, I think it alternates depending on this value of Q, because Yeah, for 310, I think it is diagonal. Yeah, so I think whatever you get, sometimes you need one, sometimes you need that. Yeah, there are these D subscript, and the subscript is fixed for you by the orbifolding procedure.
Okay, maybe we should.
Yeah, there's just one more.
One
Yeah,
more.
the-
You
last
mentioned your
question.
last slide, sphere of free energy. Does that have to be corrected to an effective sphere of free energy, or does it in 2 dimensions become C effective?
Yeah, we always mean F tilde, right? When we do this continuation, we always define F tilde, which is a smooth function without poles.
But in 2 dimensions, does it become C or C effective?
Oh, it's always becomes C. Yeah. Yeah, we don't know. Yeah, C effective is a beautiful quantity, but so far it seems very specific to the 2D case. Yeah, the funny thing is, for example, when you go to 3 dimensions already, even Yang-Lee, the minimum dimension is positive. So the naive thing of subtracting H min will not do anything. Yeah, so we definitely extrapolate to C. But it's very hard to do full extrapolation all the way to 2D because the function varies very rapidly. So we cannot claim precision in estimating, say, something so well below 4 dimensions. But
Thank Igor again.